Hi, today we are going to start equilibrium. And so equilibrium is going to answer the question for us on how far a reaction will go. So we've talked about how fast when we talked about kinetics, and so kinetics will control the rate of a chemical reaction. Now we're going to look at the extent of a chemical reaction, and those two concepts are not related at all. So you can have a really fast reaction that doesn't go to completion, and you can have a really slow reaction that goes to completion. And so the rate has no effect to the extent of a reaction that will happen. And what we're going to cover today in part one is we're going to look at dynamic equilibrium. We talked a little bit about dynamic equilibrium when we were talking about solution chemistry. We're going to write chemical formulas that relate equilibrium to the chemical reaction. And here we get to use stoichiometry, so this is kind of nice. And we're going to introduce a new constant called the equilibrium constant, which is big K, and then we're going to do a bunch of problems with big K. And so before we start that, let's just think about what this means from a chemical reaction standpoint. If you have a reaction, is it going to go to completion? So typically when we write a chemical reaction, we would write our reactants here, then this is our reaction arrow here, which indicates that there's a chemical change that's happened, and then we have these products. And so this reaction, when I write this single arrow here, this means that it's going to completion, and it's also happening in only one direction. So my reaction is going forward. In this case, A and B are my reactants, C and D are my products. When you have an equilibrium reaction, you don't have this very simplistic look at a chemical reaction. In an equilibrium reaction, oftentimes what's happening is you have a reaction that can go forward, and I'm going to draw that by a half arrow, and you can have a reaction that's going in reverse, and I would draw that by the other arrow. And so when you see this kind of arrow here, this means that this reaction does not go to completion, and it can go in two directions. It is written as if the reaction is going forward. I'm writing this as if A and B are my reactants and C and D are my products, but it can also go in the other direction, in reverse. And so in reverse, then C and D would be my reactants, and A and B would be my products. And so this is an equilibrium reaction. Equilibrium reactions will not go to completion. And so what that means is that in an equilibrium reaction, we have amounts of all substances are present. Up here, if I had this and it was set up so that I didn't run out of anything, at the end of this reaction, I would only have C and D present in this sort of completion single reaction here. But in an equilibrium reaction, even if it favors the products, I'm still going to have A and B present. And so in an equilibrium reaction, you have to take into account all the substances, meaning reactants and products, which can make it start to get a little bit complicated. Now, if I mix A and B together, there's going to be an initial thing that happens where A and B will react, and I'll be going forward, and I'll produce C and D, and then I'll get to the point where A and B stop reacting. And so I produced C and D, and then if I were to look at this reaction and I were to measure concentration changes, at time 0, I mix A and B together. At this point, this is going to go in the forward direction, and I'm going to see product produced. At some other point in time, and it doesn't matter, and it's going to be dependent upon the chemical reaction, how much time it's going to take to get there, I'm going to have a scenario where if I measure all the concentrations of all the components, so A and B and C and D, and I look at the concentration of all of these, what I'm going to see is that there's no change in concentration. At that point, that means that I'm not favoring the forward direction, and I'm also not favoring the reverse direction. And it looks like at this point, when there's no change in concentration of any of the substances, that the reaction has stopped. If I were to measure my concentrations of A and B, A would have whatever my initial concentration is, B would have my initial concentration, and C and D would have zero concentration, right? Because I'm just mixing these together. I have these initial concentrations, A and B are starting to form. They're going to form in the forward direction to produce C and D. So then some amount of time is going to happen, and now I'm going to look at my concentrations, and what I'm going to see is I'm going to have A and B present, but now A and B are going to be less than the initial concentration, and I'm going to have a concentration of C and D. And what I look at is, am I to the point where those concentration values are not changing? If that's the case, then at that point, I've reached equilibrium. At this point in time where my concentrations of any of my substances aren't changing, I've reached equilibrium. And at equilibrium, that means that I'm not favoring one direction for the reaction. We call this dynamic equilibrium. And it's called dynamic because it's still happening. This reaction hasn't stopped. But what has stopped is an appreciable change in any of the concentrations. So at dynamic equilibrium, A plus B are reacting to go forward to produce C and D, but at the same rate, C and D are going backwards to produce B and A. And so those two rates are the same. So I could say that my forward rate, I'm going to give that little rate constant K1, and my reverse rate, little constant K2, at dynamic equilibrium, K1 equals K2, and so my forward rate, the speed at which that reaction is going forward, is going to equal my reverse rate. So the reaction hasn't stopped. This is important point. The reaction hasn't stopped. It's just that the rates are now equal. And so we can't really see at the molecular level what's happening. We can only look at the concentration changes and have that imply what's happening in that chemical reaction. And so for us, it looks like the reaction has stopped. It's very static, but it really hasn't. It's still very dynamic, but we just aren't seeing a change in the concentration because it's reached the state of dynamic equilibrium. It illustrates this really well. So here would be a slide that represents a dynamic equilibrium. At time zero, I only have my reactants. I have hydrogen gas here, and I have iodine, and I only have that. So I haven't started the reaction yet. I'm at time zero. Now, if I look at what happens at about 17 seconds, is hydrogen and iodine are starting to form hydroiodic. Here at about 32, I'm starting to form more, and then here at 47, looks very similar to what was happening at 31. So what this tells me is that before I get to right around in here, I probably reached some point where I've reached dynamic equilibrium. So the reaction is still happening. It's just not seeing an appreciable change in the products. At dynamic equilibrium, this product might be breaking up and forming the reactants, whereas the reactants are going forward and forming products, and they're at the same rate. And so if you were to measure, look at the concentration changes. So this light blue line is hydrogen gas, and we're looking at the forward direction here. So hydrogen gas is a reactant, iodine gas is a reactant. What you see is as the reaction proceeds in time, these are going to start to go down, right? Because initially, this is my initial concentration I'm going to have. The forward direction of that reaction is going to happen. My concentration of these two reactants is going to go down, and then it's going to plateau. And where it plateaus, I don't see that change. That indicates that I have reached equilibrium. And this reaction could sit here for 2 minutes, it could sit here for 5 years. The concentration of my reactants at this point are not going to change unless I do something to that reaction. And we'll talk about that at the end of this chapter in part 3, what those things are that we could do to change this equilibrium scenario here. But in the absence of doing that, my reaction is going to get to here, and it's just going to reach this dynamic equilibrium. The reaction itself hasn't stopped. It's still going forward. It's just the forward rate and the reverse rate are going to be equal to each other. So for us, we don't see a change in the concentration. All right, so that is dynamic equilibrium. Point where you've mixed your reactants together, they have produced product, and then at some point the rate forward equals the rate in reverse, and then you don't see a change anymore in concentration of any of the substances in your reaction. Now you're at dynamic equilibrium, and that reaction will just sit there. N2O4, dinitrogen tetroxide gas. That can exist in an equilibrium scenario with the formation of nitrogen dioxide gas. And so this indicates that this is an equilibrium. So one of these will produce two of these, and two of these will form together to make this. And so at dynamic equilibrium, my rate forward is going to equal my rate in reverse, and that's indicated by this double arrow here. So sometimes you'll see it written this way, sometimes you'll see the arrow written this way. So my rate forward, if I were going to write my rate forward would look like this. So this would be my rate constant, and this would be the change in concentration of my reactant. My rate backwards, or reverse, would look like this. I have rate constant, and this is my rate constant forward. This is my rate constant in reverse, and this would be NO2 squared. And so those would be my rates, my rate forward and my rate in reverse. At equilibrium, these are going to be equal to each other. If a step for a chemical reaction was fast, that it reached equilibrium, and then we set these equal to each other so that we could get intermediates out of the rate law. So we're going to move away from rate law, and we're going to look at how we can talk about the concentration of all the various species that are in that reaction in terms of an equilibrium. And this is called the law of mass action. And this allows us to relate the concentrations of all the substances in a chemical reaction. It has a new component, large K, capital K, is my equilibrium constant. Now remember, when we were talking about rate, my rate constant was little k. So now we're going to have large K. And large K is going to be unique to the chemical reaction, just like my rate constant was unique to that chemical reaction that was happening. My equilibrium constant is going to be that way as well. And I'm going to be able to write this law of mass action, which relates concentrations to K. So it relates these two things together. So the law of mass action. So let's say I have this reaction, AA plus BB, and it's an equilibrium, goes to CC plus DD. So now I can use stoichiometry for equilibrium, which is nice. So we couldn't use it for rates because oftentimes we had chemical reactions that were happening in multiple steps, and one of those steps could really drive the rate of that chemical reaction and control the speed. Whereas here in equilibrium, we don't really care about how things are getting, like how many steps are happening, because we're going to look at the reaction once it's reached equilibrium, and the concentrations of all the substances are not going to be changing. So we don't really care how it gets there, we're just going to look at it once it reaches equilibrium. The law of mass action is going to allow me to take big K, and I'm going to set that equal to this here. And I'm going to always put my products on the top and my reactants on the bottom. And so even though this is an equilibrium reaction and I can write it going forward and I can write it going backwards, I'm going to set it up to be written as I have my chemical reaction. So I'm going to set this up so that my law of mass action is going in the direction that I've written the chemical reaction we would normally look at how it's written. And since I'm looking at concentrations, I'm going to look at the concentrations of all of these. So my concentration of C, product C, and remember these brackets mean molarity, my concentration of D, which is my other product, and then I'm going to take my stoichiometry here and I'm going to apply that by making my concentrations go to the power of the coefficient. And then my reactants are going to go down here. And then my stoichiometry here would be little a, little b. And so all this is going to equal my equilibrium constant here. So if I apply it to this reaction here that I wrote, big K would be equal to my products, which would be NO2 squared over into O4. And these would be my concentrations at equilibrium. So not my initial concentrations, these would be my concentrations once that's reached to equilibrium and the reaction looks to me like it stopped because your concentrations aren't changing. That's the value that would plug into here. So this would be my concentration in units of molarity, and then this would be the concentration at equilibrium, which does not equal my initial concentration. Okay, so some of it has reacted. So anytime I put a concentration value into this equation here, it's always going to be your concentrations at equilibrium, not your initial concentrations, because my initial concentrations, these would be 0 and these would be whatever I started with, and I would be dividing into 0. And so this law of mass action would not make sense. Let's do another example. Let's say I have H2 plus I2 is in an equilibrium scenario with the formation of 2HI. Let's say I want to write my law of mass action. I'm going to start with big K. I'm going to put my products in the numerator, so that's HI. I'm going to take them to the second power. In my denominator, I'm going to have hydrogen to the 1, and I2 is the 1. So these don't have, their coefficient here is an understood 1. So this would be my law of mass action. So an important point is at equilibrium, these concentrations are not changing. So K will not change at equilibrium. This is independent of my initial starting concentration. So these are all equilibrium, equilibrium, equilibrium. So this is independent of my initial starting concentrations. It doesn't matter if I start with 1 molar H2 or 5 molar H2 or 1 molar I2 or 5 molar I2. When I reach equilibrium, the ratio between my products and my reactants is going to be the same, irrespective of how much of them I started with. And so my K value will be the same as long as my reaction conditions, temperature is the same. Temperature can affect your equilibrium constant, and we'll talk about that toward the end of this chapter. But as long as my temperature is the same and I'm running these chemical reaction under similar set of conditions, I can vary my initial starting concentrations of here, and my K is going to be exactly the same every single time. Because K is independent of the initial starting concentrations, this is eventually going to come to some sort of equilibrium scenario, which is always going to have the same ratio between reactants and products. And so that allows K to always be the same. Let's talk about the magnitude of K, what K means. So if K is large, let's say we'll go back to this very simple chemical equation. So let's say K is large. What does that imply for the extent of the chemical reaction? How far is the chemical reaction gone? If K is large, if you think about it, K is large, that means that N2O4 is going to be relatively small compared to NO2. So if K is large, then N2O4 is going to be much lower than NO2, and it's going to favor the forward direction, meaning as it's written. So if K is large, I'm going to favor this direction, meaning that the majority of my reactants have gone to product, but not all of it. So it hasn't gone not to completion, but rather it's favoring that forward direction. So there'll be more product present than reactant. Now, if K is small, I have the opposite. K is small. What that means is that I have more of my reactant than I have of my product. And so this fraction here is going to be small. So if K is small, then N2O4 is going to be greater than NO2. And I'm going to favor the reverse direction of that reaction because I have more of this in solution than I have this. I'm going to favor the reverse reaction. I'm still not going to go to completion because it's an equilibrium reaction, but now I have more reactant present than product. So your magnitude of K can tell you something about that reaction, how far that reaction is going. The larger your K value, the more you're favoring this forward direction. The smaller your K value, the more you're favoring this direction. And so K is always going to be a positive value. It can be greater than 1. It can be really small. It can be 0.0000004, but I'm still going to have a little bit of product present even in a really small K scenario. So we're looking at chemical reactions here, but this also goes with solubility, acid-base dissociation, complex ion formation. All of that are equilibrium scenarios. Okay, so I'm going to show you an example. When I talk about this independence of K to your initial concentrations and how K isn't going to change, even if I change my initial starting concentrations of my reactants, my K is going to be the same. I'm going to show you a slide that supports this. And so in this slide, what we have is, this is my reaction. H2 plus I2 goes to 2HI. I've done this reaction 1, 2, 3, 4, 5 different times. So 5 different experiments all at the same temperature, so 445 degrees Celsius. These are my initial concentrations. So my first reaction, I started with a half a molar of each of these, and I didn't have any product in the mix, so I just mixed these two together. I'm going to initially start and go forward, then I'm going to reach equilibrium. And so if I had a way to measure my equilibrium concentrations, this is what it would look like. So I'd have 0.11, 0.11, and then 0.78. If I write my law of mass action, this is going to be fairly large because what I see here is that, relatively speaking, I have a little bit lower concentrations of my reactants left and a lot of concentration of my products, so I would expect K to be relatively large. And it is here at 50. 50 is a large K. Now I'm going to do this reaction again, only I'm going to do a different set of conditions. Here, I'm going to have no initial starting concentrations of my reactants, but I'm going to have 0.5 molar of HI. And then I'm going to measure over time what happens. And so now I'm looking at this reverse reaction because I started with 0 concentration of these and a higher concentration of my product. What I see over time is I'm going to reach equilibrium. So I'm going to go in reverse. I'm going to produce H2 and I2. And then this is what my concentrations look like at equilibrium. When I plug those into the mass action, I still get the same equilibrium constant. So I can do this 3 other ways. I can start with this equal amounts of concentration of all of my substances. So I take 3 gases, I mix them in together. I'm going to reach equilibrium. My ratios are going to be the same. My equilibrium constant is going to be the same. I can start with more HI or more H2 and no HI, but I still end up with the same ratio here and the same equilibrium constant. Or I can start with more I2, no HI, I still end up with the same equilibrium constant. So as long as I carry these out at the same temperature, my initial concentrations are irrelevant. The only thing that's going to allow me to determine the extent of the reaction is this law of mass action, which is going to look at the difference between the amount of reactants that are there and the amount of products that are there that are at equilibrium. We can do things to chemical reactions to manipulate them. I have a set of conditions and the reaction is written in the forward direction, but I want to see what happens if the reaction is written in the reverse direction, and I want to apply that to a constant, like say equilibrium constant. So there's 3 ways that I can relate K and the chemical reaction. And what I mean by this is I'm going to manipulate the chemical reaction. So I'm going to manipulate this in some way on paper, not experimentally in the lab. And I want to know, how is this going to change K? How will that change K? And we did this a little bit with enthalpy, if you remember in our chapter on solutions. If we reverse the reaction, then we would change the sign of the enthalpy. So this is going to be very similar. We're not going to be reversing signs because K is always going to be positive, but we're going to be able to find our new K depending upon what we're going to do to that chemical reaction. And so the first thing is just kind of reversing it. I'm going to consider this reaction here, A plus 2B, and this is an equilibrium. Everything in this chapter is going to be equilibrium. 3C, and this, I've written this in the forward direction. And so if I write my law of mass action for this, I'm going to have my products to the 3rd power over my reactants, and this would be K forward. Now let's say I want to know what will K be in the reverse. So I could write this in reverse, so my reaction in reverse would look like this. And so that would be my K reverse. Or I could just write this as 1 over my K forward. So this would be my first relationship. If I want to flip the reaction and I have a value for this, instead of trying to recalculate that value, I could just relate it this way. My K reverse is going to be equal to 1 over whatever my value for K forward is. So this is my first relationship here. So if I'm given this value, let's say K here was 6, forward, and I want to know what would be my K value if I'm looking at this reaction in reverse, then my K in reverse would be 1 over 6. All right, that's the first one. The second one, if I'm doing something to a reaction where, let's say I'm multiplying it or dividing it, A plus 2B goes to 3C. So we'll go back to this. And my K for this is, now what if I want to multiply the reaction by 2 for whatever reason? I have a reaction and I'm going to multiply it all by 2. So then I'm going to get 2A plus 4B goes to 6C. And now I want to know what is my K value for that. So my K new, this would be my K new and this would be my K original. So I'm still going in the forward direction, but now I've multiplied all the substances in my reaction by 2. So my K nu then would be C to the 6th A squared B4, and I could recalculate this. If I had these equilibrium concentrations, I could plug these in and recalculate it, or I could just say this is also equal to my original squared, or I could say this is equal to my K original squared. And so that's another relationship. So if I'm going to multiply a chemical reaction all the way through, I'm going to multiply my coefficients here by a number, then I can just take my original K value and take it to the nth value of whatever it is I multiplied by. So my K original to the n equals K nu. So this is another relationship here. You could always just plug these in and solve for them as well, but if you're given your K forward value here, you can just take 1 over that to get your K reverse. Here, you don't need to plug everything back in. You can just take your K original to the nth power, whatever it is. If divided by a half, then this would be n equals 1/2, and then that's going to give me my new K value. My third one has to do with adding chemical reactions. So we've done this a lot. This is kind of called Hess's law, where we can add multiple steps of a chemical reaction to get an overall reaction. And I can also apply this to K. So this would be our third relationship. Let's say I have this set of reactions. Little a plus a goes to 2b goes to 3c. So now my overall reaction happens in 2 steps. If I add these steps together, I get A plus 2b goes to 2b plus 3c. Now I have an intermediate here. Right, so this is my intermediate. So it's produced and then it's consumed. So my overall reaction is A goes to 3C. And so, but I have these 2 steps that happen. This would be K1 and this would be K2, and I want to know what is K overall. So I'm going to take 1 and 2 and I'm going to combine them together. So K1 looks like this, B to the 2nd power over A. K2 is C cubed over B squared. And then if I want to know K overall, I could just multiply these 2 together. So K overall is equal to K1 times K2. So if I multiply these together, what you see happen is K overall is going to equal to B to the 2nd A times C cubed B to the 2nd. And what you see what happens with the intermediate is the intermediates cancel out and I'm left with C cubed over A, which would be the overall rate that I would write for the reaction. So I also have this relationship here. If I have the K values for 2 individual steps, I don't have to calculate the K overall. I can just multiply these 2 individual K's together to get my K overall. So those are the 3 ways I can apply relationships. I can compare K forward and K reverse this way. I can manipulate a chemical reaction by either dividing or multiplying by a number, so then my K original would be to the power of that. That's going to be my K nu. Or if I have multiple steps, I can multiply my individual K's for each of those individual steps to get my K overall. So those are the 3 ways that I could calculate K if I was manipulating a reaction. So I only need to use these if I'm manipulating this reaction on paper and I want to know how it's going to change K. So that's where the look at these 3 here might save you a little bit of calculation time, so you can understand these relationships between them. Let's say I have this reaction here. Nitrogen gas reacts with hydrogen gas in an equilibrium reaction to form ammonia at 25 degrees Celsius, and my K value at that temperature is 5.6 times 10 to the 5th. So this is a large K. This is, if I were to write that out of scientific notation, K would be 5, 6, and then 4 zeros. That's a large K, which means this is going to favor the products. Just if I see a K that large, that's kind of what I'm thinking in the back of my brain is I'm going to have a significant amount of product left at equilibrium and probably very little of this. So let's apply these relationships to this. So let's say I want to calculate the reverse. Let's say what is the K value for the reaction in reverse. Remember, because K values imply the forward direction. Even though this is equilibrium, when I write my law of mass action, I'm writing it as if it's going in forward direction. So these would be my product, these are my reactants. what is the k value if I want to look at this in reverse, then I can just take k reverse equals 1 over k forward. So that would be 1 over 5.6 times 10 to the 5th. And then the other thing I'm going to do to this reaction is I'm going to divide it by a half. So I want to look at it in reverse, and I'm going to divide it by half. So this is the reaction that I want to find the k value for. So the first one is I reversed it. So now I have k in reverse. My reaction is in reverse. And what I've done is I've taken this whole reaction and I've multiplied it by a half. So my k nu then is going to be to the 1/2 power. So I'm going to take my k original and I'm going to take it to the n for my new equation is going to equal 1.3 times 10 to the minus third. So I applied relationship 1 and relationship 2. We will stop here and pick up with part 1b in the next video.